Hello guys, MJ here with MBJ Knowledge. You're welcome to the series of magnetism. This is the part 2. If you haven't watched the part 1, please I'll leave it in the description. Make sure you watch the part 1 of magnetism. So today we're proceeding with our lesson and we're going to look at the methods of magnetization. Okay, so uh, we're going to look at a number of methods for magnetization. So the first one that we're going to look at will be the stroking method. Okay. In this context, what does stroking mean? In this case, to stroke, we're going to look at it means to rub something against. So in this case, when you want to magnetize a magnetic material, if you remember, we defined the magnetic material as a material that can be attracted by a magnet, meaning it can also be formed or be made into a magnet. So what we are trying to do here, we are trying to introduce the ability to attract in that particular material. So the first way or the first method we can use is a stroking method. All right. The second method is an electrical method. Now between these two, the most effective method to make a permanent magnet is to use an electrical method. All right. So now let us look at what the stroking method is all about. Okay. So stroking method, you use a permanent magnet and also a magnetic material. So how do you make a magnetic material or how do you form a magnetic material into a permanent magnet with the use of a permanent magnet? Okay, so you stroke or rub the permanent magnet against your magnetic material. All right, so now that material, you should remember that a magnetic material composes of what we call as the dipoles. Okay, dipoles are these are particles inside the magnetic material that act like a magnet. All right, so they've got, in fact, they behave like floating compasses. All right, so those dipoles, if it is not a magnet yet, they face in different direction. So now, because they are facing in different direction, it means that material is not yet a magnet. So for you to make it into a magnet, it means the dipoles inside that particular magnetic material, they're supposed to face in one direction. They need to change into a magnet. So notice what is happening. You bring your magnet. So we take this one as a magnetic material with the dipoles inside. Okay, so these black arrows inside here, they are representing the dipoles. Okay, the particles that behave like floating compasses. So when you bring in a permanent magnet, let's say this is a permanent magnet, and then you bring in a north pole. That's the one you're going to use to stroke against this magnetic material, meaning rubbing against. So you rub like that, okay? What happens? These materials inside this magnetic material will gain the magnetic field. All right, they will be affected by the magnetic field and they will flip and face in one direction. Okay, check. After doing that, those materials or the particles inside that magnetic material, have you seen here on this second diagram? They will face in one direction. This here will form this material into a magnet. It means this material has now become a magnet because the dipoles are facing in one direction. Now, here, the end, so we are using a north pole. This is our end right here, our right hand side. That is where the stroking is finishing from. That end will acquire an opposite polarity. When you say opposite polarity, meaning it will acquire an opposite pole to the one which is stroking. So what is stroking is a north pole, meaning this side here, for it will be a south pole. Definitely the left hand side will be a north pole. That is how you can use a stroking method to form a magnet. Let us look at an electrical way of magnetizing or forming magnets. All right, so if a question comes to say, explain or write an experiment to magnetize a steel bar or maybe an iron. The first statement you're going to write will be a steel bar is placed inside the solenoid through which direct current is passed for a while. So for you to make those dipoles to face in one direction, if you're using current, don't forget the type of current we're using is direct current, a current that goes in one direction. So first of all, talk about the steel bar being placed inside the solenoid. All right. Second, you're going to say a strong magnetic field is produced. Remember, a solenoid behaves like a magnet when current passes through it. So because of that current that has been passed through, there's magnetic field which will be produced or generated inside that solenoid. What will happen to the steel bar? Because there's magnetic field, those dipoles will rearrange and face in one direction. That is the reason why we are saying the steel bar is done what? Magnetized. The last point, which is the most important or critical point, is that when you view it at an end of the bar, now the end we are talking about is the right hand side, your right hand side. If current is going in or flowing in the clockwise direction, okay, that end becomes a south pole. Let's just look at this diagram here. So I'm talking about the current. Now, when you look at this diagram, it has got a battery here, okay? This is a combination of cells. So this is a battery, this is a resistor, a rheostat, okay? Then we have arrows. So current is going in this direction. This is clockwise direction. Now, how do you know that this current will go in the cells? The polarity on the cells. So the longer line here is representing a positive, a shorter line is representing a negative. So current moves from the positive to the negative. So in case in the exam, they say, can you form this end to become, let's say this is end A, they say, can you make this end A to become a north pole? Then what will happen is that you are going to change the polarities here. It means the positive is supposed to be on your right, okay? It means the arrangement of the cells will change. The positive is supposed to be here, the negative is supposed to be there, so that current now moves in the anti-clockwise direction. So always remember, when you're writing down your statement, if they specify to say they want this end to become, then make sure the polarity on the cells, you change them. Okay. So that is about that. Then let us look at the methods of demagnetizing. Okay. We have a number of methods that we can use actually to demagnetize. Demagnetizing simply means to remove the ability to attract in a magnet. Okay. Magnetizing, it means you are dealing with the magnetic materials. Now here we are dealing with a magnet. So we want to remove that ability, the magnetic field in that material. Okay. So we have, we can use either heating. Of course, they are not effective. When you heat a material or when you heat a magnet strongly, okay, by use of anything that you can use to heat it, an example is a Bunsen flame, the magnet will lose its magnetism very quickly. So what happens, remember with the dipoles, so since they are facing in one direction, when you're heating it, you're confusing the dipoles inside that magnet. Hence, when you continue doing that, they will face in different directions. Okay? The second way is the demagnetization by hammering. When you're hammering, okay, again, you're disturbing they will gain the energy, that is the heat energy, as you are hammering. Okay, the kinetic energy will increase, hence causing those dipoles to start moving, because they will gain that energy and they will become excited. In the end, they will flip and change and face in different directions. Okay, so it will become very weak. All right, so that is one way. Then now let us look at using an electrical method. How do you demagnetize using an electrical method? In this case, when magnetizing, we are using direct current. Okay, why? Because we want those to face in the same direction. A question comes, when you're demagnetizing, why do we use alternating current? Alternating current has no specific direction. It changes direction every second. So this will confuse, because if you are demagnetizing, it means you have to confuse the dipoles. They need to face in different directions. So in this case, you write a statement. The first statement is, you say a magnet to be demagnetized is placed inside the solenoid. That's the first step. Number two, the solenoid is connected to an alternating current supply. When you're demagnetizing, make sure, don't forget, you're supposed to use the alternating current. Okay? Third, the magnet is withdrawn far away through the solenoid, okay, in the east-west direction, while the alternating current is still flowing. When you write these three statements and draw up this diagram, then you are set. Okay? Why? Because after you do that, you continue repeating that process of inserting the magnet, withdrawing, while the current is still flowing. Then the dipoles will be confused and they'll face in different directions, causing that magnet to be demagnetized. So this is the setup. So if I ask you to say, can you write an experiment to demagnetize a magnet? Make sure you write these three statements, and the fourth one showing that you're supposed to repeat that the three statements. Again, you draw up the diagram. Very important, because for you to get the 4 marks or 3 marks, the diagram is supposed to be shown. Then this is the symbol for alternating current. Don't draw those cells. The cells don't give alternating current. They give direct current. So this is the symbol that you are going to draw representing your current supply, which is alternating in this case. Okay. Then let us look at magnetic field. Okay, so magnetic field is just a region around a magnet where magnetic effect can be detected. Okay, so magnetic field is a region surrounding your magnet. There, you would find that when you bring in any magnetic material, even if it is not in contact, but it is just closer to the magnet, you'll be able to feel the force of attraction, that material being attracted. So that region around the magnet where the magnetic field can be felt, that is what we call as the magnetic field. All right? So there are two methods that we can use for us to observe the magnetic field of a bar magnet. All right? So we're just going to look at one, which is the plotting compass. Why are we using the plotting compass? We'll explain. Okay? So the first step for you to understand, okay, so if you have a magnet here, we are trying to know the direction in which the magnetic field they point. Okay, they point from where to where, or they are running from which pole to which pole. That is why we are using a plotting compass. So in this case, you use a small plotting compass. Okay, you place it near one end. You can pick whichever end. Okay, assuming you have a magnet, you can pick either the north pole or the south pole, whichever end. So you indicate that one as X. Okay, the compass needle is marked with dots. Okay, so when you place it, let's say this is point X, we put a plotting compass here, you're going to mark that end as 1. You remove it, put it on a different position, you mark that end as 2. Okay, the compass is shifted to position Y with the south pole of the needle pointing to dot 2. Okay, so this simply means you're using this position X as your north pole. Okay, so this pointer, it has got a material of iron, and you know the property of iron, it quickly gains the ability to attract. So what happens, this needle actually gains the ability to attract, meaning it becomes a magnet. So this is the south pole, where the needle, the arrow is, that's the north pole. So north pole and the north pole will repel. No wonder we're saying the south pole pointing to dot number 2, meaning the south pole will be the one which will be attracted to the north pole. All right? So the position of dot 3 is marked. This process is repeated until the compass reaches the other end of the magnet, until the plotting compass reaches this other end. So you'd find that still more, the plotting compass, the needle is still pointing towards this other end where we're going. Okay? Then you join those dots with an arc, like that, to obtain the magnetic field. This is what you can get, like this diagram that you are seeing here. So in the end, you are going to have magnetic field. Now, since the North Pole was the end which was taken as the initial point, look at what the plotting compass is doing. It is pointing away towards the North Pole. Reason why it means the pointer here is a North Pole on this compass. This side where there is no point, it is the South Pole. So now, remember the property of poles. Like poles, they attract. So in this case, the south and the north, they are attracting. That is why the North Pole is repelling and pointing to a different direction. Hence, it shows that the magnetic field lines, they are running or pointing from the north to the south. All right? So the properties of the magnetic field lines are that, number one, they point from the north to the south, as you can see. So always it is from the north to the south. That's where the arrow is pointing to. Then they never intersect with each other. When you look at these, there are spaces in here. Okay? So this indicates that the magnetic field lines, they repel each other sideways. That is the reason why they do not intersect. Okay? Then the higher the density of the lines in a region, the greater the magnetic field line. Meaning a greater strength of magnetic field, just know that there the density will be greater. It means you have a lot of lines for magnetic field, then the density is high. Okay? So watch out for the next lesson. Make sure you don't miss out. Thank you very much for watching up to the end. Don't forget to subscribe and share, and I'll leave the link to the first video of our series.